All right. Well, let's get started then. My name is Brooke Smith. This webinar about designing a rectangular concrete beam using the newly released AS3600 2018, the Australian standard for concrete design. As a bit of an outline, I'll be going through first an brief introduction, then give you a broad overview of what the major changes are in the 2018 revisions. I'm not going to go through every detail, but the major changes I will go through. Then the meat of this presentation is going to be discussing the full design process for a rectangular concrete beam, including flexural, shear, and deflection checks, as well as your quicker checks for stability and crack control. I'll do 2 example beam calculations, and then finally conclude and answer any more involved questions that anyone may have. So first, a bit about me. My name is Brooke Smith. I'm a chartered professional engineer, master's degree, Engineers Australia member. I'm also licensed as a professional engineer in the United States. Some of you may notice my accent. I did grow up in the United States originally. I'm currently the lead engineering developer for ClearCalcs. We recently released an updated concrete beam calculator for 2018. I spent a good chunk of time working on updating that. And so since I've had my head in the 2018 codes for a while, we figured we'd give a webinar discussing the updated standards and communicating all of that to you. Previously, I also have experience as a forensic structural engineer, specializing in reinforced and post-tension concrete, held a research fellowship in the system behavior of thin-walled steel, and have a number of publications and journals and conferences from that. And more recently, I worked in research and development consulting and structural engineering, specializing in cold form steel. So today's goals, I hope that all of you will be able to walk away from this webinar being able to design a rectangular reinforced concrete beam to the new AS3600 standards. Now, in order to fit within a roughly hour time frame for this webinar, I will be making a couple of simplifying assumptions. Usually these are going to be true, but keep them in mind. First is that there are no torsion forces. I'm assuming that no demand and torsion. I'm assuming no pre-stressing and no post-tensioning. I'm going to be going through a rectangular concrete beam for simplicity, but I'll point out a couple of important spots where T-beams differ. I'm only going to be broadly, as I mentioned, going through the changes from 2009. The goal of this webinar is to teach you to design according to 2018, not to go through every possible change that happened. I'll also only broadly be going through some of the detailing requirements. Provisions for detailing are pretty prescriptive, depend upon your full structural layout in many cases, and are generally relatively easy to follow. A couple notes, we'll be distributing this slide deck as well as a video from the webinar afterwards, so you can look for that in your email. And please feel free to ask any quick questions as I go. I'm able to see the chat and question and answer screens as I'm going through this. I'll answer any quick questions that you have while I'm still on the topic. If something is considerably more involved, I'll wait until the end to answer that. So moving on to an overview of the major changes since 2009. First, fee factors have been revised, your capacity factors. Generally, they've been simplified and many have been increased. Shear procedure has been pretty significantly redone, especially for the shear strength of concrete. The rectangular stress block formulas have been modified actually twice since 2009. Deflection calculations have been modified, adding an alternative simplified method for non-pre-stressed concrete, as well as modifying the effective moment of inertia calculation. Shrinkage and creep calculations have been pretty heavily revised. Now, there are some other changes that have happened as well outside the scope of this webinar, so I'm not going to be discussing them. But if they concern you, you may wish to look at the provisional changes in punching shear, steel fiber reinforced concrete, some of the detailing provisions, fatigue, and diaphragm action of concrete. So first, the fee factors. Many of the limit states have been increased by 5%. That's particularly for anything that involves ductile reinforcement. So shear and torsion for most cases, and I'll go through exactly what most means later on in this presentation, has been increased by 5%. Tension's been increased by 5%. Compression for everything, regardless of the reinforcement, has been increased to 0.65. And bending without axial has also been generally increased. Class L, if you have Class L reinforcement, you've been switched from a formula to just a flat 0.65 factor. And those of you a bit more eagle-eyed with your formulas here will notice that for Class N reinforcement, it's exactly the same thing plus 5%. Shear procedure has been pretty significantly redone to the point where you should basically forget all the equations that you previously learned, especially for shear of concrete. As I mentioned, I grew up in the United States, so I was looking through this and recognized a number of the equations in there. They largely adopted the same procedure that the United States American Concrete Institute uses for calculating concrete shear capacity. Generally, that's a simpler procedure. So many of you may remember having to calculate a beta 1, beta 2, and beta 3 factor for your shear strength of concrete. That's no more. It's replaced by just a simple KV factor, and we'll go through the details of that later on. There are also some more explicit alternate clauses for non-pre-stressed beams, and torsion was formerly a separate section entirely. In the standard, it's now been merged into shear as part of shear, and you should generally be considering the combined effect of torsion and shear at once. Rectangular stress block formulas have been updated actually twice since 2009. They were already modified in the A1 revision of 2009 and have been further modified for 2018. Overall effect is that the strength of the concrete will not be changing the shape of your stress block as much as it used to. Deflection calculations have also been modified. The effective moment of inertia equation has been changed. Mathematically, it's similar, but not quite the same. 2009's A2 revision already added in an alternative, simpler set of equations for non-pre-stressed beams. 2018 fixes an important mistype that they had in there. Hopefully none of you fell victim to this, but parentheses are important. B effective and D are both supposed to be in the denominator there. D is not a numerator value. Shrinkage and creep have also been revised. Shrinkage uses basically the same equations, but the factors have been simplified and made a little more conservative. Not sure if any of you are listening in from Adelaide or Perth, but if you are no longer arbitrarily lumped into the category of elsewhere. Everyone now, regardless of where you are in Australia, takes a epsilon CSDB factor of 800 times 10 to the negative 6. Creep was almost completely revised in 2009's A2 revision. 2018 adds a further K6 factor to try to account for nonlinear creep at high stress. So moving on to the overall procedure for designing a rectangular beam. First, you'll need to calculate your demands by AS1170. I'm not going to be going through the details of that here. We'll do that in another webinar sometime later on. But for designing a concrete beam, the limit states that must be checked include flexural capacity for both your positive and negative moment. Usually that means at your midspans and then again at your supports. You need to check shear capacity and deflection. And then you have some usually very quick checks for stability and crack control that need to be verified. So first, before you can do much of anything, you need to make sure that you have some of your derivative values for the basic geometry figured out. That includes your total area of tension, compression, transverse steel, the depth to your longitudinal bars, the outer layer of your longitudinal bars, ratio of elastic modulus for steel and concrete, gross second moment of inertia, and gross cross-sectional area. So first step in flexural capacity analysis is to use your pure mechanics that you learned back in uni days for calculating the uncracked beam. This is essentially an elastic composite beam calculation, and you'll need it later for the minimum bending strength calculations in flexural code. So you transform the area of your steel to an effective area of concrete, essentially transforming the graphic on the left here to the graphic on the right. Calculate the location of your neutral axis, sum the areas times the centroids divided by total area, and then use parallel axis theorem to get your total effective or total gross uncracked second moment of area. And then in the end, you end up with a section modulus. That section modulus you're going to use later on in your minimum bending strength calculations. So then ultimate capacity for flexure, we move back to the code, and that's based upon rectangular stress block theory. So code gives you calculations for the alpha 2 and gamma factors. Those are factors that define the magnitude of your stress block. Alpha 2 is your magnitude, and gamma is a proportional factor for the lower extent of your rectangular stress block. Rectangular stress being the area of concrete that is in compression. The code won't give you a formula for calculating KU. They're expecting you to figure that out by mechanics. For a rectangular section, it's equal to the equation that I've shown here. You're essentially ratioing your total tension and compression forces. You'll end up with an ultimate moment based upon the simple formula at the bottom here, total tension force times the distance to the centroid of compression. So then you have to check a couple of minimums here. You have the minimum moment capacity that's required. And the code gives you this equation shown at the top here. PE has to do with pre-stressing. We're assuming no pre-stressing. So without that, it simplifies down to simply 1.2 times Z times F prime CTF. F prime CTF being a property of your concrete, having to do with the flexural tension strength of concrete. Now, you have to meet that minimum moment unless your failure will not lead to a reduced collapse load or to sudden collapse. For reinforced beams, that means you simply need to have a minimum quantity of tensile steel, equal to the equation shown here. For a rectangular section, your alpha B factor in this equation is simply 0.2. For T-beams or L-beams, there are separate formulas that are given in AS3600. Now, the overall effect of the minimums defined here is that you need to meet one of the two equations shown here. And usually it's going to be the second one that you meet, but you can meet either. So finalizing for your flexural capacity, you're going to check that your concrete won't crush. That is, that strain in the concrete will never exceed 0.3%. For an under-reinforced beam, which is what you're usually going to be designing, that means this formula here. That means that your steel will yield, and at that yield strength, concrete strain is still below 0.3%. The AS3600 also defines a limit for your KU value of 0.36, and you cannot exceed that unless a couple of other clauses are met. Most important being that you have to have compression reinforcement if your KU is greater than 0.36. And that also has to do with helping prevent concrete from crushing, helping prevent brittle failure from happening. You then calculate your phi factor, and as we mentioned, that's been increased in 2018. So you end up with a final capacity of phi times mu. Moving on to shear, for most flexural beams, you can design shear by the sectional design method. There's an exception if you're near discontinuities. If you are, you need to use the strut and tie method, and I will refer you to the codes for that. We have not yet included that in our new concrete design sheets in ClearCalcs. because it's not very common. But if you do actually have discontinuities you need to consider, you have a more complex shear method that you need to work with. So first, for the sectional design method, you need to calculate your effective shear depth. That means a maximum of either 72% of your total depth or 90% of the depth to your longitudinal tension reinforcement. I'd urge caution with here, make sure that you use the correct little d value. It needs to be the d to the reinforcement that is in tension at the location you're considering. So for most cases, you're going to be interested in shear near the supports, which means that the top longitudinal reinforcement is going to be what's in tension. So make sure that you're using little d to the top reinforcement for your shear near supports. For a rectangular beam, your effective breadth is simply equal to the total breadth of the beam. For a T-beam, it's going to be equal to the breadth of the web only. Shear fitments. The term fitments is what's commonly used in the code. Many of you will more commonly be using the term ligatures, same thing. You need to use those fitments if either your shear demand is greater than the factor concrete capacity demand, or in any case, if your total depth is greater than 750 millimeters. There's then a minimum cross-sectional area for the fitments defined in the equation shown here. The shear capacity of the concrete, I mentioned this was completely redone in the 2018 codes. Your main equation is shown at the top here. It's simply a kV factor times your effective breadth, effective depth of in shear times root F prime C. Usually you can use a simplified method to calculate kV. Usually means for any time you have reinforcement with a yield stress of at most 500 megapascals, concrete strength of at most 65 megapascals, and a maximum aggregate size of at least 10 millimeters. So that's going to be pretty common. That will usually be the case that you can use this. If that's not true, you have a notably more complex method of calculating kV. So that kV value for a reinforced beam is calculated based upon whether you have more or less than the minimum transverse steel. If you have more than it, your kV is a flat 0.15. If you have no transverse steel or less than the minimum, then you have a simple formula for calculating kV. Now do keep in mind there are a couple of mandatory, essentially sanity checks you need to have for your shear capacity here. That is, if creep, shrinkage, and differential temperature together make up more than 10% of your total stress in the concrete, you need to consider it explicitly and use a slightly more complicated calculation scheme. Usually that's not going to be the case. I'll talk to you a little bit about how you can very quickly estimate what creep and shrinkage effects are. And second, if you have a significant load reversal that can cause cracking, then you can't take concrete shear strength into account at all. The only time that's going to happen is typically going to be if you have very, very high uplift forces. So perhaps if you're in major cyclonic regions in Queensland, this might be the case. Usually it's not, but if you just keep this in mind if you do have major load reversals. So in the steel capacity, again, in most cases, as defined with previously for a maximum yield strength of the steel, maximum strength of the concrete, your theta V is taken as 36 degrees. Theta V is the angle of inclination of a shear crack that is expected to happen. So this is calculating the resistance strength against those shear cracks. Alpha V is then the angle of the shear fitments themselves. Usually they're going to be 90 degrees, but you can incline them as well. Those of you a bit more eagle-eyed and remembering your trigonometry will notice that the two equations shown in the AS3600 are actually exactly the same equation. If you plug in 90 degrees to the second one, you get the first equation. Now you can only include the strength of the steel for resisting shear if you have at least the minimum fitments. So if ASV is greater than or equal to ASV min. You do have one final check to make sure that concrete won't crush. And that is an equation, a pretty prescriptive equation given here. This is an overall maximum for shear strength. Usually it's not going to govern, but it may possibly. It will typically only govern if you have a very slender beam. Total shear capacity will then be the minimum of either the sum of contribution from concrete and contribution from steel, or the total maximum. And yeah, I do see someone has raised their hand in the webinar. If you do have a question, please just ask it by chat. We'll do some voice questions later on, but it's a bit easier for me to address and prioritize questions if you ask them by the chat here. Anyway, calculating your phi factor for shear. For most cases, your phi factor is going to be 0.75. And the conditions on that are if you have class N fitments and if you are not being governed by concrete crushing strength. So essentially, if ASV is greater than ASV min and if VU is less than VU max, then your phi factor is 0.75. Other cases, you take it as 0.7. So in general, for deflection, you have three possible methods given in 3600. You can use a refined method, which is quite complex. You have to take in all strain properties from shrinkage and creep calculated quite accurately, as well as staged construction effects. We don't deal with that. And it's rare that you will have to, but that method is available. There's a deemed to conform method where you have set span to depth ratios and such, or there's a simplified method. We're going to use a simplified method. It's likely to be your most common and is actually just about as complex as the deemed to conform method. So it's almost, you may as well use it. For the simplified method, you do have a short-term deflection and a long-term deflection. Short-term deflection is based upon calculating an effective second moment of area. For reinforced beams, you have a single formula for that. This formula looks a bit long, but it's actually not terribly complicated. The only variable that we did not discuss in this is B effective, your effective breadth. For a rectangular beam, that's just equal to your total breadth. For a T-beam or similar, it's going to be equal to the breadth of the web. And then for long-term deflection, there are two methods of calculating that. The more accurate method is to calculate shrinkage and creep individually and add those to the total effects of all of your loads. That's often a bit of a tedious process. We're not going to use it here, and we don't yet make it available, but it's to come. We're going to use the estimate factor. Likely, especially for residential construction, you're likely just going to use that as it is a considerably simpler method. It's just a simple formula for KCS. And then your long-term deflection is equal to the short-term deflection plus KCS times short-term deflection. That's calculated at the midspan for interior spans, and for if you have a cantilever, you need to calculate it at the support. So technically, you should be calculating this amplification factor, this KCS, for each individual span that you have. And for each cantilever, in most cases, all of your interior spans are likely to be the same, so it's likely that you're only going to be calculating this once. But keep that in mind if you have cantilevers or if you have differing interior spans. So next you have some quick checks that you need to make for stability and for crack control. First, for stability, you can do a full stability analysis, or there's a deemed conform methodology. Usually you're only going to need to worry about deemed conform, and that will cover almost all cases that you have. If you have a continuous slab or floor or similar, then you can completely ignore this because you have continuous restraint. If you have discrete restraints on your beam, then you do need to consider this and just quickly check this. For an interior span, you have an L1 value, that's the distance between your lateral restraints. And then the ratio of L1 to the effective breadth of your beam must be less than the simple factor given here. For cantilevers, you have a separate calculation. The clear projection of your cantilever ratio to your effective breadth must be less than the ratio and value given here. And then for crack control, usually you only have two relatively straightforward clauses that you need to meet. You usually means for any beam that after construction of your building will be fully enclosed within the building envelope. And also that cracking will not affect the function of the beam. So if those two things are true, if it's fully enclosed and cracking won't affect function, then you only have to meet these two requirements. First being that you have at least minimum tension steel, and second being that you have fairly generous maximum spacing between your longitudinal reinforcement. At most 100 millimeters from the edge, and at most 300 millimeters center to center spacing. If you're designing beams bigger than this, you might need to reconsider your beam design. Shrinkage and creep. I mentioned that these have been revised in 2018. Shrinkage, we're not going to go through the detailed calculations for these. There are relatively detailed calculations that you can make to do these accurately. But the simplified method is typically going to be just looking at the table provided in the code. Table 3172 for shrinkage will give you a final design shrinkage strain. And this is pretty good for just doing an estimate check on, you may recall, the 10% maximum effect that you can have defined for shear. You should be checking this table quickly and making sure that your strains aren't going to exceed significantly more than what you would expect from your normal loads. Creep is effectively an amplification factor multiplied onto the strain due to sustained loads, so strain due to permanent loads. You can typically just look up that final creep coefficient, again, in table 3183 in the code. And you should be doing this in most cases. Just, again, make sure you're not going to exceed that 10% stress threshold. So now moving on to some examples. We'll do two different examples, one a simply supported beam and two a more complex beam. First, we're just going to take just about the simplest possible beam you can imagine. There's only tension reinforcement, simply supported, 3.5 meter total span. We're going to have a imposed load and a permanent load on it, equal to 1.5 and 0.9 kilopascals, respectively. We'll assume this beam is in an office building. That's affecting the character of the imposed load. We're going to assume no transverse shear reinforcement, a load width of a simple flat 1 meter, and concrete strength of 32 megapascals. Now, we're going to show how the methodology and formulas work using our new reinforced concrete calculator in ClearCalcs. So I'll load up my web browser. And just go over to clearcalcs.com. And I'm going to create a new project, just call it webinar for now, and add in a rectangular concrete beam on here. So at the top here, we're making similar assumptions to what I described in our webinar already. No torsion, no pre-stressing, and I'm going to assume that basically you're going to be checking all the detailing on your own. That's not checked in this sheet. So for the simplified beam, our total dimensions were 300 depth, 130 millimeter total breadth, 32 megapascal concrete, 3.5 meter length. And we said we only have tension reinforcement consisting of 3 N12 longitudinal beams. So no top reinforcement, no transverse reinforcement, a 1 meter load width with 0.9 and 1.5 kilopascal dead and live load respectively. We'll keep self-weight in there. Character of imposed load, we said this was an office building. And usually you'd be considering wind and some other loads as well. I'm going to be removing those from this just to simplify everything. Again, we'll address complex loading later on in another webinar some other time. And then we end up with final result. 75% of our total capacity calculated. Our controlling factor is long-term deflection. And you can see how demands and capacities relate to each other in a summary box at the top here. Now this sheet is going to follow through the full procedure we just described. So flexural strength calculated at the midspans. It's going to calculate your uncracked neutral axis location and depth to neutral axis with KU. You'll notice similar formulas as we went through in the webinar earlier. This is as typical an under reinforced beam. Shear analysis. I mentioned that that VU max is not usually going to govern for you. Here it's calculated as 259 kilonewtons, whereas our capacity of the concrete is 26 kilonewtons. So we're very far off from that web crushing limit actually occurring. That's typically going to be the case for you. And deflection analysis, calculating the effective second moment of area. And we have just our quick stability checks at the end as well. So we see that moment is pretty far from governing. Shear is at 42%. If we had roughly double that shear, we may want to consider starting to add some fitments. But in the end, it's going to be the long-term deflection that's governing here. So then going to our second example, that's going to be a more complex beam. We're going to assume that the first beam we calculated is resting on top of our more complex beam at a location of 7 meters. We're going to have a total 10 meter span length, or excuse me, total 10 meter beam length with spans of 3.5 meters, 4.5 meters, and then a cantilever on the end of 2 meters. We'll have two different sets of reinforcement that differ between positive moment and negative moment, and 12 bars on the top and 10 bars at the bottom. In positive moment regions, we'll have 3 N10s at the bottom and just 2 N12s at the top. Negative moment regions will have 3 N12s at the top and 2 N10s at the bottom. This time we'll assume it's a retail building. We'll put in some basic R6 shear fitments at 200 millimeter spacing. Increase our load width a little bit to 1.5 meters. And we'll again use a 32 megapascal total concrete strength. So going back into our calculator, duplicate that so that we don't need to re-enter in our section shapes, which is the same depth of 300 millimeters and 130 millimeters. This time our total beam length is 10 meters. So we'll put in that. Supports at 3,500 millimeters and 8,000 millimeters. for our 3.5 and 4.5 meter spacing. You can see those shown graphically in the lower right here. Said we were going to have N10s on the bottom and N12s on the top. This time we are including top reinforcements in positive moment regions in the midspans here. But we have three longitudinal reinforcement beams on the top and 2 on the bottom. Shear fitments, we are going to include those. R6s at 200 millimeters. These are going to be typical standard fitments that have 2 legs, just your standard closed rectangular fitment, and 90 degrees for a perpendicular fitment. And then this time we do have differing reinforcement in negative moment regions. So this is going to copy from what we already entered up above, but we're going to modify it a little bit for our negative moment regions to instead have 3 top reinforcements and 2 bottom reinforcements. Same loading, except we're going to increase the load width to 1500 millimeters. And we're also going to link in the previous beam that we calculated and all the reactions due to that and put that in at 7 meters. We then have a retail character imposed load instead of an office character imposed load, and including self-weight as normal. Now you notice at the top here that we did have a failure due to our stability checks. Scroll down here. Our default assumption for stability checks is incorrect for our multi-span beam. So we just need to enter in that it's 4,500 millimeters, the maximum length of our span, and that works just fine. We no longer have a failure there. We can see again here that we're making a bit more productive use of our flexural capacity. Still a lot of space there, but we're using about 1/3 of our flexural capacity in both cases. Deflection is what's going to be controlling for us. We have a yellow shown here for being above 90%, but that still works. And making a bit more use of our shear capacity here at 54%. All right. And then moving back to the bulk of our webinar. That concludes our examples. So going to concluding the presentation and answering any other questions we have, sort of summing everything up, there have been some major updates made to the phi factors, to shear, to rectangular stress block calculations, to deflection, and to shrinkage and creep. We went through the full beam design process for a typical rectangular concrete beam. So for flexure, that means using your mechanics to do an uncracked beam analysis, rectangular stress block calculations per the code, then checking some minimums as well. Shear, calculate the effect due to your concrete contribution, which was completely redone for 2018. Steel contribution, and then make sure that you will not have concrete crushing due to shear. Deflection, calculate your effective second moment of area, then calculate your long-term factor. And then stability and crack control, you have some quick checks for that on span to breadth ratios and minimum and maximum quantities and spacings of steel. We also performed 2 examples with simply supported and complex beams here. So at this point, I'll invite you to ask any other questions that you may have. And you may feel free at some later time to check out this calculator, as well as a broad range of calculations that we have at ClearCalcs.com for timber, steel, concrete, connections, retaining walls, and soon to have cold form steel, some more advanced connections and foundations. We'll also be providing some more free webinars such as this later on for other types of members and connections. So keep an eye out for those, and we hope that everything will be beneficial for you. I do see one question here asking how the new concrete shear strength generally differs in magnitude from the 2009 code. I've not gone through a lot of examples with that. It will typically, I believe, be slightly larger, but it's going to vary. Yeah, I'm sorry, I can't answer that too well for you. I'm not, yeah. All right. Yeah, I'm keeping an eye to the questions being asked in the chat here, so feel free to ask anything you may have. Yeah, this presentation will be available for download later on. Give us a day or so to process it and make it available to you, but you'll be emailed with links for everything. In the ClearCalcs platform, we will eventually be implementing C-sections. Cold form steel C-sections are going to be very soon on our list of things to be added. Hot rolled steel C-sections will also be added in the near future as well. Yes, percent reinforcement is available in the concrete calculations. That is available in the detail mode in our ClearCalcs sheet. And I'll just reopen that moment. So if you expand to detail mode, you'll see your fraction of steel. We will eventually be adding raft footing designs. Unfortunately, we do actually have a relatively long list of things we'll be adding. So that will be probably a month or two down the line, but that will be getting added as well. From Fiona, yes. The 2009 requirement for including shear steel if V star is greater than half of VVU, yes, that has been removed. It's been replaced to simply you only need to include shear steel if V star is greater than phi VUC. Your phi factor times the contribution from concrete. In ClearCalcs, yes, you can calculate the reinforcement required for any type of loading. We include loading calculations for any type of load, for your wind, earthquake, snow, and you may include triangular or point loads or concentrated moments as well. And this will calculate the amount of steel required regardless of what your loading is. So continuing to look through the questions here. I'm sorry if I'm missing anything as people are typing multiple questions through here. Yes, the beta 3 factor has been entirely removed. All of the beta factors have been removed. There's no beta 1, beta 2, or beta 3. It's just been entirely replaced by KV. So you're not specifically accounting for high shear near the supports anymore. We do not yet take into account moments for steel connections, but that is actually currently in production. That should hopefully be available for you for bolted and weld connections in the next couple weeks. Not entirely sure what the asker here means with the difference between flexure shear and shear. There are different shear procedures for beams versus columns, or for if you have tension in combination with shear. But yeah, it's the same thing for any type of beam. All right, so it looks like most of the questions. If you do have any other questions, you may feel free to contact us. My email address directly is brooks.smith@clearcalcs.com, or you can email our main address at hello@clearcalcs.com. And we look forward to working with you in any of your future calculations. And again, please keep an eye out for future webinars we'll be holding for other types of members with other materials and other types of connections and loading details. Thank you very much.